Hi class, in this video here we want to talk about the second derivative test. And what the second derivative test is, it's an alternative method for identifying relative extrema. So it can identify relative extrema. And now we already have a method for that, right, using the first derivative test, but this is just another way to do it. And it's and I'm going to walk you through the test here. And it's actually, once you get used to it, it's actually really quick to use the second derivative test, and you'll see. Okay, so let's start off by, let's let f be a function that f prime of c is equal to 0. So what's going on here is this c is a critical value or critical number. And the second derivative of f exists on an open interval that contains this c. So we have a relative min and we have a relative max. And the second derivative test is as follows. If f double prime of c, so the second derivative, you take the critical number and you plug it into the second derivative. If that value is greater than 0, then it turns out f has a relative minimum. I know you would think of max because it's greater than 0, but it's actually a relative minimum at the point c f of c. And if f double prime of c is less than 0, then f has a relative max at c comma f of c. Now, if f double prime of c equals 0, then the test actually just fails. It's inconclusive. That is, f may have a relative max, a relative min, or neither. In such case, what you're going to do is then you're just going to use the first derivative test. Okay, so these two options here are the most important, okay? So we're going to use these to apply the second derivative test to find relative extrema. So I'm going to work through 3 examples on the coming slides here for this. All right, so I'll keep jumping back to this, so we'll have this handy as we go through this. So here's what we want to do. In this first example, I want to find all relative extrema of the function, and let's use the second derivative test where applicable. Okay, so f of x for our first function here will just be some polynomial function, 4x minus x squared. Okay, so the first thing we have to do is we have to find critical numbers. Okay, so to do that, what we're going to do is take the first derivative. So this ends up just being 4 minus 2x. And what you're going to do is now set that equal to 0 and solve. So you're looking where the first derivative is equal to 0. We're just going to add the 2x over. Divide by 2. And so you have a critical value here. Okay, this is my critical number. Okay, I got my critical number. So now what I want to do is I want to use this second derivative test. All right, so I'm going to need to find the second derivative to do that. Okay, so this is real easy. If you take the second derivative, all right, so the derivative of the first derivative, it's actually just negative 2. Okay, so it's just a constant function, actually. So what you're going to do is you're going to take your critical value and plug it in. Okay, so this critical number, you just plug it in, and that's going to be equal to negative 2, which is less than 0. Okay, so I took my critical number, plugged it in the second derivative, and it came back negative. So what that means here, look, when the second derivative evaluated the critical value is less than 0, okay, then what you have is you have a relative maximum, okay, at this c f of c. So thus, we have a relative max at this point, 2 comma f of 2. Well, f of 2 here, excuse me, 4 times 2 is 8 minus 2 squared, so 8 minus 4. So at the point 2 comma 4. Well, let's just make sure this works. So let me grab my graphing calculator here and show you that it worked. So what I'm going to do is I'm going to take this function and I'm going to plug it in, right? So 4x minus x squared And look, well, yeah, absolutely, we have a max there. And it looks like it is actually at that 0.24 that we just found. So this works. So the second derivative test worked, and it identified for us the extreme value of the function there. All right, let's do one. Maybe that's a little bit harder. Okay, that's going to be a little bit more algebraically intense. All right, so here's the function now. All right, we want to do the same process. Let's look at f of x is equal to the square root of x squared plus 1. All right, so again, first thing, I'm going to actually even rewrite this as x squared plus 1 to the 1/2, because sometimes you're going to notice as I work through the problem here, I'm going to interchange between these two notations. Sometimes it's easier when you're going to take the derivative to use this form. All right, so let's find critical values or critical numbers. So the first derivative, you have to use the chain rule, right? So I'm going to bring the 1/2 down. This is x squared plus 1. 1/2 minus 1 gets me the minus 1/2. And then the derivative of the inside is 2x. Well, look what happens. 1/2 and the 2 cancel. And then I have x. And this comes down, right? Because it's a negative exponent, as the square root of x squared plus 1. Okay, so I'm going to set this equal to 0 and solve. So I have x over the square root of x squared plus 1. That's equal to 0. So the denominator here doesn't matter. It actually, if you were to cross multiply, cancels out, right? And it can never be, you can never have an x vice, so you're going to divide by 0. So really, you're just left with x is equal to 0. All right, so I've got my my critical number here. So now I'm going to use the second derivative test. Okay, so I need to find the second derivative. All right, so this is my first derivative. Okay, I'm just going to rewrite it. So I'm going to have to use the quotient rule here. So it's the derivative of the numerator, which is 1, times the denominator, which is the square root of x squared plus 1, minus the numerator times the derivative of the denominator. Okay, so you're gonna have to chain rule this, right? But we already know what the derivative of this is, right? The derivative of this is right here, because that's what we found. Like, even if you need to chain rule it again, right? So the 1/2 comes down. X squared plus 1 to the 1/2 minus 1 is minus 1/2. 2x. All over this squared. All right, so now let's clean it up. Okay. This is the square root of x squared plus 1. Handwriting's getting a little terrible here. Minus, well look, 1/2 goes away with the 2 here. So then I have x times x gets me x squared all over, and then this comes down, x squared plus 1, all divided by, here, square root squared cancels, x squared plus 1. All right, so I need to clean this up. And basically what I'm going to do is I'm going to combine the numerator here. Okay, so another way you could think about it is you're going to multiply this by the square root of x squared plus 1 over the square root of x squared plus 1. Watch what will happen when I do that. I'm going to have to go to the next slide for this, but I'm going to distribute it here. Okay, so square root of x squared plus 1 times square root of x squared plus 1. Well, look, the square root and square roots are going to cancel. I'm just going to be left with x squared plus 1. Minus, now when you distribute here, they cancel out. Square root of x squared plus 1, and the denominator cancels with this. So you're just left with minus x squared all over. This here is to the first power, and then times the square root would be x squared plus 1 to the 3/2 power. And now look what happens here. X squareds cancel, and you're just left with 1 divided by x squared plus 1 to the 3/2. That's my second derivative. So now what you're going to do, now that I have my second derivative, I'm going to take my critical value, which is 0, and plug it in. Well, that ends up just being 1 over 1 is 1, which is greater than 0. So what that means is we have a relative, now going back, it's greater than 0, so we have a relative min. So at the point it was 0, f of 0. And so when you plug 0 into our original function, you get 0 squared plus 1 is 1, square root is 1. So we have a relative min at the point 0, 1. All right, and just recall, this was for our function, the square root of x squared plus 1. Let's verify that just so you can so you can see, right? So let's load up our graphing calculator again. So let me clear out what we had in here. The square root of x squared plus 1. And when I graph it, yeah, look, boom, you can see right there. Isn't that awesome? You can see that the relative min is at 0, 1. So this really did it. It's really, really perfect here. Okay, let's do another one. Let's do a crazy one here. All right, so let's find the relative extrema for this one right here. All right, so let's look at f of x is equal to x over the natural log of x. All right, and so just looking at this, we see that the domain, you can't have a negative, you can't have 0 or a negative number in the natural log here. So the domain is just the domain of the natural log, which is that right there. All right, so the first thing you have to do is find critical values. So to find the first derivative, what you're going to have to do here is you're going to have to use the quotient rule. All right, so f prime of x, derivative of the numerator, which is 1, times ln of x, minus x, and then the derivative of ln of x, we know it's just 1 over x, right? All over ln of x squared. So cleaning this up, you have the natural log of x, minus 1, all over ln of x squared. Okay, that's my first derivative right there. So then what I have to do is now find critical values. So we're going to take this and set it equal to 0 and solve. So again, the denominator doesn't matter. Okay, so you're just looking, when does the numerator, when does ln x of 1, ln of x minus 1 equals 0? So I add the 1 over. And then, knowing our rules of exponents here, I'm going to take e and raise it to or our rules of logs and exponentials here. I'm going to raise each side to the e, or take e and raise it to each side of the equation here. The e and the ln will cancel, and you'll just see that x is equal to e to the first power, which is just e. So x is equal to e. This right here is my critical value. All right, so what I have to figure out now is okay. I know I have a critical value or critical number at x is equal to e, but is it a relative max? Is it a relative min? I don't know. So what we have to do is we're going to use the second derivative test. So on the next slide here, what I'm going to do is I'm going to rewrite the first derivative. So we saw that f prime of x is equal to ln of x minus 1 all over ln of x squared. So f double prime of x, you're going to need to use the quotient rule here again. So the derivative of the numerator, well, the derivative of ln of x is just 1 over x times the denominator, which is ln of x squared, minus, this is where things get crazy, the numerator, ln of x minus 1, times the derivative of the denominator. So bring the 2 down, I have ln of x, and then you have to find the derivative of the inside, which is 1 over x, which is a lot, right? Which is a lot going on, all over this squared. So ln of x squared becomes to the 4th power. Okay, so what are we going to do here? All right, notice they each have a 1 over x, so I'm going to factor that out. They each have an ln of x, so I'm gonna factor that out, right? So when I do that, okay, what am I left with here? So I have an ln of x here, minus, and then in parentheses, ln of x minus 1 times 2, okay, because notice I factored out an ln of x and an x over here, all over ln of x to the 4th. Now this is where, a lot going on here, but let's clean it up. So the 1 over x, the x comes down, and an ln of x is going to cancel here. So this ends up being just ln of x, and then I'm going to distribute. Minus 2 ln of x, and then minus becomes plus 1, and then I have this 2. So plus 2 all over x ln of x cubed, because this one canceled with one of them here. So then I'm just going to clean this up. Ln of x minus 2 ln of x this ends up being just 2 minus ln of x all over x ln of x cubed. All right, so my critical number here was x is equal to e. So if I plug that in, f double prime of e, this is 2 minus ln of e over e ln of e cubed. All right, well, what is that, right? Ln of e is 1, so that's all 1. So this ends up just being 1 over e, which is greater than 0. So what we know here is then this function, right, when it's greater than 0, has a relative min at the point e f of e. Well, if you look back here, what is f of e? That's just e over ln of e, which is e over 1, which is just at the point e comma e. And you could quickly verify that in the graphing calculator too, but there was so much algebra here and so much math that you can see, like, you have to be meticulous, and it's so easy to make a mistake somewhere and it just throws everything off. So as you work through these problems, just make sure you take your time and you work through them very, very slowly.